Good morning, children. Today we're going to do some notes on Taylor polynomials. I will probably stumble a lot over my words because this is really weird for me talking to a computer. First thing I want to talk about is what is a Taylor polynomial. It's a specific type of power series. Now, we talked about power series last class. It is a power series where we have basically a bunch of constants times a bunch of powers of x. All right, and we have two different types of Taylor polynomials. There's one that is about x equals 0, and then there is another one that is centered about x equals a. So that should sound fairly familiar because we had power series that were centered about x equals 0 and x equals a. Now, oops, there's a little box. The way that we do this, the Taylor polynomial, is we generate it using a specific formula, all right? A normal polynomial of any sort is written like this, right? So if n equals 4, for example, a fourth degree polynomial of x would be called f4 of x, meaning we're going to have 4 powers of x. So this would be c0 plus c1 times x. C's are constants, right? Plus c2 times x squared plus c3 times x to the third plus c4 times x to the fourth. And it would stop there because that's the fourth degree polynomial. Remember, C just means the first constant, the second constant, the third constant, etc. So for a Taylor polynomial, we do a specific formula, all right? So we find a function of x, a polynomial of x, by generating the following terms. We have f of 0 plus f prime of 0 times x plus, oops, this keeps coming up, plus f double prime of 0 times x squared plus f triple prime of 0 over 3 factorial times x cubed plus the fourth derivative times x to the fourth over 4 factorial plus all the way up to the however many you need, all right? So it's a very simple formula to remember. Now, what's the point of this formula? Well, the point of this is you can take any function and you can actually generate a polynomial, which is the simplest type of function, to represent the function that you have. And polynomials behave in very simple and specific ways. So it is very advantageous for us to be able to generate a polynomial that represents a function. So that's what we're doing. We're just writing all these functions as a polynomial, and it's a good approximation of the function when we use these polynomials. So the first function that we're going to generate a Taylor polynomial for is 1 over 1 minus x, and the number is going to be 3. So hold on. Don't show this message again. I should have selected that the first time it popped up. Okay, so what we're going to do is we are going to go ahead and find all the derivatives that we need. Now, here's our formula right up here, so I'm going to keep that in sight. So we need to find, in order to do n equals 3, we need to find 3 derivatives to find p3 of x. All right, so I'm going to first find the derivatives. So f of x is equal to 1 over 1 minus x. F prime of x is equal to negative 1 times 1 minus x to the negative 2. And then we have to take the derivative of the inside, which is negative 1. So when we simplify this, the negative 1 times negative 1 gives us a positive 1, and we end up with 1 over 1 minus x squared. Now we're going to find all of these values at 0, but first let's do all the derivatives. So now we're going to do f double prime of x. We need 3 derivatives altogether. So that's 1 minus x to the negative 2. So when we take f double prime of x, it's going to be negative 2 times 1 minus x to the negative 3 times negative 1, which is the derivative of the inside. Again, the two negatives will cancel each other, and we end up with 2 over 1 minus x to the third power. And then finally, we'll take our last derivative that we need for this Taylor polynomial. F triple prime of x is equal to, well, this is 2 times 1 minus x to the negative third, so when we bring the negative 3 out front, we get negative 3 times 2, which is negative 6, times 1 minus x to the negative fourth, times the derivative of the inside, which again is negative 1, so we're going to get rid of our negative. And so our final answer to this is 6 over 1 minus x to the fourth. So now what we'll do is we will plug in the value that we need. Now the value that we need here is x near 0. So we're talking centered at x equals 0. All right, so when we plug in those values for x, we get f of 0 is equal to 1 over 1 minus 0, which is 1. F prime of 0 is we're going to plug into the f prime function, so that's going to be equal to 1 over 1 minus 0 squared, which is still 1. F double prime of 0 is equal to 2 over 1 minus 0 to the third, but 1 minus 0 to the third is still 1, so it's equal to 2 over 1. And so then f triple prime at 0 is equal to 6 over 1 minus 0 to the fourth, which is equal to 6. Now all we have to do is generate our polynomial. So here it goes. So P3 of x, the third degree Taylor polynomial, right, about x is going to be the following. Let me slide that down a bit so we don't get too confused. And I'm going to shrink this a bit too. Sorry kids, you know me, being a little OCD here. There we go. So P3 of x ends up being the following. It is f of 0. So I just look up at the formula. I'm not going to write all that out again because the formula is right up there above, right? So it's f of 0, which is 1, plus f prime of 0 times x, so that's 1 times x, plus f double prime of 0 times x squared over 2 factorial, plus f triple prime of 0, which is 6, times x to the cubed over 3 factorial. I just said x to the cubed. That's funny. All right, so now remember, this is really consistent, this formula, because this is actually over 1 factorial, and this is actually over 0 factorial, which is defined to be 1. So when we actually simplify this is 1 over 1, which is 1. So we have or P3 of x equals 1 over 1, which is 1, plus 1 over 1 times x, so that's x, plus 2 over 2 times x squared, so that's plus x squared, plus 3 over 3 times x to the third, so that's plus x to the third. So P3 of x for 1 over 1 minus x is 1 plus x squared plus x to the third. Now if you look at the graph on a calculator, and I'm going to ask you to do this on your own because obviously it's not easy for me to do this, but if you look at this graph on your calculator near 0, and if you look at this graph on your calculator near 0, what you will see is that they are very, very close. So this polynomial gives a very close approximation of that function near 0. All right, so that's a good thing. Now, you can see what the pattern is here. So even if you needed P5 of x right now, you could just continue the pattern, and you can have you can be reasonably sure that the pattern here will continue. So if you needed P5 of x, it would be plus x to the fourth plus x to the fifth. That is the Taylor polynomial for 1 over 1 minus x. The next one, we're going to do a Taylor polynomial about x equals a for the cosine of x. So first thing we're going to do here is go ahead and get the derivatives of cosine of x. It's always the first step. We want a third degree polynomial, so we need 3 derivatives. So f of x, of course, is equal to cosine x. F prime of x is equal to negative sine of x. Great practice here. F double prime of x is equal to negative cosine of x. And f triple prime of x is equal to sine of x. Now we want to plug in the value of a that we have. A is equal to pi over 4. So this series is centered at pi over 4, right? This is the center. So f of pi over 4 is equal to cosine of pi over 4, which is equal to radical 2 over 2. F prime of pi over 4 is equal to negative sine of pi over 4, which is equal to negative radical 2 over 2. Of course, you know your trig functions, right, kids? F double prime of pi over 4 is equal to negative cosine of pi over 4, which is equal to negative radical 2 over 2. I see something going on here. And then finally, f triple prime of pi over 4 is equal to sine of pi over 4, which is equal to radical 2 over 2. Okay, I'm getting paranoid that this isn't recording, so I'm going to bring up this little thing to see if it is. Oh, yes, it is. We're in 12 minutes in now. Oh, this is good times for you, I'm sure. So now what we're going to do is we're going to go ahead and use that Taylor series formula. Now, the only difference with the Taylor series about x equals a number is now we're going to have x minus whatever a is. Okay, so here a is pi over 4, so we're going to follow all of our primes and factorials with powers of x minus a to match. So you see that the prime, the number of the derivative, the number of the exponent on x minus a, and the number of the factorial in the denominator are all the same. See, 2 factorial, second power, second derivative. And it works that way all the way through Taylor polynomials. So it's always easy to remember this formula. I don't even have to look at it while I'm writing. So now we go on. So we're going to say, so P3 of x is equal to, well, the first thing we need is f of x. So f of x is radical 2 over 2. Next thing we need is f prime of x, right, times x minus 4. So f prime of x is negative radical 2 over 2 times x minus pi over 4 to the first power over 1 factorial. Now we really don't have to do over 1 factorial because it's 1, right? And then the next one, we need f double prime of x, which is negative radical 2 over 2, times x minus pi over 4 to the second power, all over 2 factorial. And then finally, we need plus f triple prime of x, which is radical 2 over 2, times x minus pi over 4 to the third all over 3 factorial. Okay, so you're just using these values that you get for the first, second, third derivatives, right? That's all you're doing. Now that you have that, you just need to simplify it. There's not a whole lot of simplification can be done here, but what I do is I take these 2's and I put them down in the bottom with the factorials because I just multiply top and bottom by 2. And that makes it so I just have a single fraction and not a complex fraction. That's all you can really do with this. So P3 of x ends up equaling radical 2 over 2 minus radical 2 times x minus pi over 4 all over 2 minus radical 2 times x minus pi over 4 squared over, well, you got a 2 from the top times a 2 from the bottom, so since we're multiplying those two 2's together, 2 times 2 gives us 4 in the bottom here. And then finally plus radical 2 times x minus pi over 4 to the third all over 2 times, right, this 2 times this 3 factorial. Remember 3 factorial is 3 times 2 times 1. So you have 2 times 3 times 2 times 1, which is a grand total of 12. So that's that Taylor polynomial. So if you were to type this in your calculator, and you were to type cosine of x in your calculator, and look at how they match up near pi over 4, what you'll find out is they overlap. They look just like each other because that's what this is all about. It's about approximating a function with a power series, powers of x. So let's go on to the next page. Just a really interesting thing about this, I shouldn't go off topic when I'm on the computer, but an interesting thing about this is you can always see the derivatives in here, all right? Because, for example, if I want the third derivative of our function, of our original function, f triple prime of x, if I wanted to work backwards and I was given a polynomial, that would be equal to radical 2 over 12 divided by 3 factorial. Okay, so if you take radical 2 over 12 and divide by 3 factorial, that's going to give you, no, I'm wrong, sorry, radical 2 over 12 times 3 factorial, oh, sorry, you know, your poor old math teacher, times 3 factorial, sorry about that, kids. You just have to multiply by the factorial that is in that term, and you can figure out what the derivative was from that term. So radical 2 over 12 times 3 factorial gives us radical 2 over 12 times 6, which is equal to radical 2 over 2. And that's handy because sometimes you'll be given a Taylor polynomial. And they'll say, what's the fifth derivative? And you can go to that term and multiply by whatever factorial is in that term, and you can find that fifth derivative. So that's important to note. The x minus whatever to a power never enters into it. You're just looking at the derivative and the factorial. And that works out well. So that may serve you at some point in the future. I'm not sure on tonight's homework, but it's definitely part of what you need for the AP exam. All right, so now we're going to generate this Taylor series for the e to the x. And the thing about a Taylor series is this time we're going to do the infinite series. Now that doesn't mean we need to generate infinite derivatives because just like up above, you can see a pattern after a while, and you just continue the pattern. So that's what we're going to do, and I'll show you how to do that. So when it's a Taylor series about x equals 0, when it's infinite, it's called a Maclaurin series. All right, so very important to know, Maclaurin series is a Taylor series about x equals 0. It's just a special name for the approximation near 0. So we're going to first find the Maclaurin series for e to the x over 2. All right, so I have f of x equals e to the x over 2, and then I have f prime of x is equal to 1/2 times e to the x over 2, because the derivative of e to the x of x over 2 basically is the derivative of 1/2 x. So when I take the derivative of the exponent, I get 1/2, right? So then the next thing, f double prime of x is equal to 1/2 times 1/2, which is 1/4 times e to the x over 2. And then finally, let's take one more to be sure that we have enough terms to generate a pattern. F triple prime of x is equal to 1/2 times 1/4, which is 1/8 times e to the x over 2. Now you can even see a pattern in your derivatives here. So the pattern in the series is going to be easy to determine because there's already a pattern in your derivative. So let's evaluate this. This is about x equals 0. So we're going to go ahead and evaluate these at 0. So f of 0 equals, guess what? E to the 0, which is equal to 1. F prime of 0 equals 1/2 times e to the 0, which equals 1/2. F double prime of 0 equals 1/4 times e to the 0, which is equal to 1/4. And f triple prime of 0 is equal to 1/8 times e to the 0, which is of course equal to 1/8. Now that you have all of those, we're going to actually do our Taylor polynomial. So now we say e to the x over 2 is approximately equal to, that's what the squiggle equal sign means, and we're actually going to generate our polynomial. It's the same formula, right? So it's f of x first, so it's 1, and then it's f prime of 0, which is 1/2, times x to the first power, right? It's the first derivative, it's the first power, it's over 1 factorial. 1, 1, 1, they all match. And then the next one is going to be plus f double prime of x, 1/4, times x squared over 2 factorial. Second derivative, second power, 2 factorial. And then finally, plus f triple prime of x, which is 1/8, times x to the third over 3 factorial. Third derivative, third power, 3 factorial. Now all we have to do is go ahead and simplify. And when you simplify, to find the pattern of a Taylor series, do not fix the factorials. Leave them as factorials. Okay? And then we're going to go ahead and write things as powers as well, if we can. So we're going to say e to the x over 2 is approximately equal to 1 plus x over 2 plus x squared. Now I'm going to take that 4 and bring it down over, I'm going to rewrite the 4 as 2 squared. So when I bring this 4 down, I rewrite it as 2 squared, and then times 2 factorial. And then my next one, my 8 is going to go down as well. When it comes down, I'm going to rewrite it as 2 to the third. So I get x to the third over 2 to the third times 3 factorial. Now, you're all pretty smart, right? So what is this? Well, this is this is term n. Let me put this in a different color. N in this is equal to 0, 1, 2, and 3. So, what have we got for a formula? Well, I can actually say that this is equal to any term that follows is, well, does the power on x match the n? Yes, it does. So it's x to the n over 2 to the n times n factorial. That's going to work every single time. Now go back to 0, make sure that works. Okay, so if we do it at 0, does that formula work? X to the 0 times 2 to the 0 over 0 factorial. Does that equal 1? Yes, it does. So you're in great shape. All right, it actually works for every single term, and so that would be your formula for this Taylor polynomial. So we can now say e to the x over 2 is approximately equal to the sum n equals 0 to infinity of x to the n over 2 to the n, times n factorial. These, I mean, at this point you should be thinking, okay, this isn't bad. This is, you know, it's a formula. I just plug and chug through it. Taylor polynomials are great because you're always just plugging and chugging through a formula. Oh, actually, this problem, before I move on, the answer to this problem does not ask you for the whole Taylor polynomial. It only asks you for the first 4 terms. So your first 4 terms would be here. All right, so that would be the answer to the problem. But if you had to find the whole polynomial, as you can see here, it's pretty darned easy to do. So if they ask you to generate the actual full polynomial, you can do that. Let's move on to the next page and the last problem. This one also asks for the first 4 terms. I'm also going to ignore these instructions and find a full polynomial because I think it's important for you to recognize these patterns. All right. So 1 over x is your function. So let's go ahead. F of x is equal to 1 over x. F prime of x. Remember, the first 4 terms is usually the 3rd degree polynomial because you have terms 0, 1, 2, and 3. That's important to note. So f prime of x is equal to negative 1 over x squared because it's negative 1x to the negative 2, right? And then f double prime of x, you're taking the derivative of negative x to the negative 2, so what you get is negative 2 times the negative that's already there, so that gives you 2x to the negative 3. And then finally, for the 3rd derivative, you're taking the derivative of 2x to the negative 3, so negative 3 times 2 gives you negative 6x to the negative 4, so it's over x to the 4th. Now I don't like where I put that, so let me fix that real quick. Oops, I guess it's not going to let me fix it. Okay, I'm going to win. I'm going to erase it and rewrite it. There we go, negative 6 over x to the 4th. All right, so now what we do is this is about a equals 2, so we need to evaluate this at 2. So f of 2 is equal to 1/2. F prime of 2 is equal to negative 1 over 2 squared, which is negative 1/4. F double prime of 2 is equal to 2 over 2 to the 3rd, which is equal to still 1/4. And then f triple prime of 2 is equal to, what is it equal to? Negative 6 over 2 to the 4th, which is equal to negative 3/8. So there are your derivatives. And now all you do, again, you just plug them in, right, so go ahead, plug into your Taylor series formula. It's right up at the top of the page. So we start with 1 over x is approximately equal to f of 2. Remember, this is about a equals 2, so we're going to have x minus 2 power to the power after it, right? So it's 1 over x is approximately equal to, starts with f of 2, which is 1/2. The next thing is going to be plus f prime of 2, so that's minus 1/4, times x minus 2 to the first power over 1 factorial. Remember, first derivative, first power, first factorial. And then plus the second derivative, 1/4, times x minus 2 squared over 2 factorial. And then finally, minus the third derivative, 3/8, times x minus 2 to the third over 3 factorial. And that is that. So let's go ahead and figure that out. And of course it goes on and on. Oops, forgot a plus sign. Oh no, I didn't. It's right there. Got it. So now let's simplify. Now what happens here, this is an interesting little deal. You get 1 over x equals 1/2 minus x minus 2 over 4. Now 4, of course, is 2 squared. So let's look for a pattern. Now when I put the 4 in the bottom with the 2 factorial, what kind of happens here is, well, let's look at what 2 factorial is. It's 2 times 1. So if I put the 4 in the bottom with that, I'm going to have 4 times 2, which is 8. So this looks like it might be a pattern. So instead of sticking to my leave your factorial alone business, this time I'm actually going to use it. I'm going to say x minus 2 squared over 2 to the third power, because 4 comes down, 4 comes down, gets multiplied by the 2 factorial, and you get 8, which is 2 cubed. So that's a good thing to have. I need this to move down for me for a second. All right. And then the next one, check it out. See what this is 3 times 2 times 1, right? That's what 3 factorial is. Hey, check it out. There's a 3 in the top, there's a 3 in the bottom. Let's cancel them. I know, I sound like a geek. Let's cancel those 3's. If you cancel those 3's, look what you're left with. When you bring the 8 down, with the rest of it, you got 8 times 2 times 1. Sweet, right? 8 times 2 is 16. What power of 2 is that? Well, heck, it's 2 to the 4th. So we got x minus 2 to the third, and the top and the bottom we got 2 to the 4th. Now you're set. You can tell me. You can tell me what the next term is. I know you could, right? First of all, it's, since the first term is the 0 power, right? What you have is, or the 0 index for n, right? What you have is this. Let me get my n's down there so I don't confuse you. I got a little ahead of myself. N equals 0, 1, 2, 3. Okay, so odd indexes of n's are giving you negative answers, right? So that means you're doing, to do this, you'd have plus negative 1 to the n, because odd powers are giving you negative answers. That's the way it should be, so you're good to go there, times x minus 2. Hey, look, it matches, right? 3, 3. You're good there. So x minus 2 to the n, I should put, and then over, well, it's not 2 to the n, but it's darn close, right? It's 2 to the n plus 1. And that's it, right? That's pretty simple stuff. Now, remember, all they ask for in these and on most of your homework problems is the first 4 terms. So, first of all, that shouldn't be an equal sign. It should be an approximation sign. But then the first 4 terms that you will need for your homework are right here. But it's always good to be able to generate the whole series. Now, if I wrote this in summation notation, it'd be the sum n equals 0 to infinity of negative 1 to the n times x minus 2 to the n over 2 to the n plus 1. And that is it, kids. I'm done with you for today. Your homework is here. If you have major questions on the last homework assignment that we did, I will address those tomorrow. I will take 1 or 2 questions maximum. The answers are posted online for everything, so please check those answers and try to work your way through them, but you should be in pretty good shape. So homework 462, 1, 3, 5, 9, 11, 13, and 27, and I will talk to you tomorrow. Have a great day.